So last week we introduced this notion called amenability. And one way to apply the amenability is in terms of the operator algebra is really related to their group C-star algebra. And that's what we're going to do this week. So first of all, I need to introduce a little bit background on the C-star algebra. And if you actually took the operator algebra course, the Pure Math 810, you've probably already seen this. So let me just give a quick definition. So let's recall a Banach algebra. So Banach algebra basically is a Banach space with a multiplication and a norm. So let's call it A, and it has a norm. So we call it a C-star algebra. If it satisfies a extra condition, so if it satisfies for every A inside this A, if I compute the AA star, so that's A star is the involution on the Banach, I should say Banach star algebra. The A star is involution, and then you multiply. As a Banach algebra, you know this one should be less than equals to the product of their norm, but in a C-star algebra, this is actually equality. So if you just make this equality, and that has to equals to the norm of a square, which is also equals to the norm of a star square. Okay, then this is called a C-star algebra. And this identity sometimes is called the C-star identity. So if a norm satisfies such an identity, then we call it a C-star algebra. And of course, if your algebra A is sitting inside some B of H, for example, the operator on the Hilbert space, then automatically you take the A star, basically the adjoint of your operator. Then it is clearly because the basic operator theory, you can see why they satisfy these. So clearly, if you have A, which is a norm-closed subalgebra, of some bounded linear operator on some Hilbert space. So here H is a Hilbert space. Then this A is indeed a C-star algebra. So A is a C-star algebra. That is just basic operator theory on Hilbert space. And in fact, the converse is also true. If I give you an abstract Banach star algebra equipped with a C-star identity norm, then you can actually construct a Hilbert space, and this A can be realized sitting inside this B of H for some H. All right, so that's the C-star algebra. We're not going in that direction. It's just some basics. You'll see the proof in A10. But the one thing we talk about, one common example of C-star algebra is related to the group. So we call it a group C-star algebra. And there are actually several ways of building a group C-star algebra. So first of all, let's consider the following. So if let's just say G is a locally compact Hausdorff group, and we actually see how we can build some L1 of G, which is a Banach star algebra, and we talk about this representation. So if you recall, if I have a unitary representation G from G to say U from G to B of H, that actually corresponds to a non-degenerate representation or star representation of the Banach algebra L1 of G to the same B of H. Basically, this is the theorem we talk about when we do the compact groups. So we talk about the integration and disintegration. So starting from a unitary one, and you can integrate it to a star representation of the L1 space. And the converse is also true. If you have some non-degenerate star representation, you can always decompose it into a unitary representation. So this way, you kind of embed the L1 of G inside some B of H, and that's where you can build your C-star algebra, because C-star algebra are essentially the subspace of the B of H. So what you can do is that you say, well, let's just pretend the L1 is inside this B of H. So for every F inside the L1 of G, so you can define a norm. Let's call it the pi norm using this one particular representation. So this is a star representation, and you just let it to be the pi of s. Okay, so you say, well, this is pi of s. It's an operator in B of H, so we used that as the norm of this L1 of G. And we just pretend the L1 of G sitting inside B of H, and we close it up. Well, it may not be closed. So let's just close it up. And because the way this pi is a star representation, and the right-hand side of B of H is some B of H, so clearly this defines a C star norm. Okay, so this satisfies a C star identity, so it's a C star norm. So what we can do is that we can build a C star algebra this way. So let's say C star pi of G to be, so I take the image of the L1 space under my star representation, and I just take the norm closure, thinking about it as a subalgebra inside the B of H. It's clearly going to be a subalgebra closed under the adjoint as well. So that's going to be a C star algebra for this one particular representation. And of course, for each representation, technically you can do this procedure, but there are really just two kinds of representation that are kind of natural for your group. So there are two natural objects. So natural objects. So the first one is, as you can see, the one we study the most is the left regular representation. So if I let lambda to be the left regular representation, then what I can do is that I just let C star lambda of G to be the lambda. Well, lambda is a left regular representation. Well, you can think about it as the G onto the bounded linear operator on L2 of G. But as we saw, if you have a unitary representation on this L2 of G, you can pretend is also a star representation of your L1 of G. So you take lambda, you take the image of this L1 of G, and you close it up inside the norm of the sitting inside the bounded linear operator on the L2 of G. So that way you get a C star algebra. So this C star algebra is sitting inside a very concrete bounded linear operator Hilbert space, so basically the L2 space. And then you take B of the L2 of G. That's where your the C star algebra sits in, and this is called the reduced C star algebra. So this is called the reduced C star algebra of your group G. Okay, so the reduced. So sometimes you write a C star lambda of G. Sometimes you even write a C star R of G. So sometimes it's called the C star R of G. Sometimes called the C star lambda G. Either case, okay, that's your reduced one. So it's a pretty concrete one. Okay, you have a L2 of G, you know where the space is, and the second one is kind of the universal object. Okay, so the left regular is just one particular representation, which is just the natural, probably the easiest representation. The other one is more like the universal one. So what you can do is that you let the pi of u to be the direct sum of all the irreducible representation pi of your group G, and then you take a direct sum. So this one you can treat it as a sitting, so it basically maps from G to the direct sum of all this B of H pi, or you can think about it as a linear operator on some really big Hilbert space, okay? And but this is going to be a representation, so this is kind of bigger than all the other irreducible representations. So it has certain universal property. So what you can say is, well, let's define the universal C star algebra or universal group C star algebra to be the C star algebra generated by this pi of u. Okay, so you take pi u of the L1 of G, and you close it up. Okay, you close it norm closure. And this Hilbert space is going to be huge, okay? So usually it's super big. And while sometimes you can make it smaller because the norm may not depend on all of it, maybe it just depends on a few of them. But in any case, it's a really abstract one. There's another way of saying this is that you can think about this. So if you take any f inside L1 of G, the universal norm, the U norm, okay, you can really just equals to this pi of U of f. But this pi of U, because it's a direct sum of all the other irreducible representation, you think about this, basically all the star representation of the L1 of G will be in there. So this is also going to be equals to the supremum of the pi of f, where pi is a star representation of the L1 space, L1 of G. Okay, so they're basically the equivalent and equivalent definition. Okay, so because your pi u basically contains all of these other star representations, so it's certainly the supremum of them. Well, you can also define it, you can just ignore the pi u and you just define f of u to be the supremum of this norm, and you can track it's also C star norm, and you close it up into that norm, and you also get a C star algebra. That's another way of doing that. But in either case, you can build a really large kind of abstract C star algebra. So this is called, so this C star U of G is called the universal. So sometimes it's also called the full C star algebra or full group C star algebra. I should say group C star algebra. And sometimes I write a U here, or sometimes also denoted by the C star of G. Okay, so I can just, if I don't write anything in the subscript, then it just means the full or the universal one. And because it's universal, because you see the norm is really the biggest norm you can put on the L1 space. Basically, it's the biggest C star norm you can have. So basically, if you have any, say, pi a representation, a star representation, say non-degenerate, then if you consider the full C star algebra, then you can map your f inside, say, L1 of G, sitting inside this universal one. You can map it to the C star pi of G. Okay, so you can just map it there because the full one, the norm is always bigger. So the f inside the full one, because it's the universal one, the norm is bigger than the f inside the pi norm. Okay, pi is just one star representation. So you always have a onto homomorphism or star homomorphism between these two C star algebras. Okay, so there exists a onto star homomorphism of from your universal one or the full one to the C star pi of G. Okay. So basically, that justifies why sometimes it's called the universal ones. This is essentially in the category of the C star algebra. This is the kind of the universal objects for the group C star algebra. All right, so basically now we have these two objects. One is really concrete. You build an operator on the L2 space, you get the reduced one. And the next one is the universal one, which is kind of the abstract one. You take the direct sum or build it on the really large space. And these two sometimes are actually the same. Okay, so here is the big theorem we're going to prove. We're going to divide it into several steps, but the big theorem is that this is actually related to G being amenable. So in fact, G is amenable is if and only if the full C star algebra, the universal object, is the same as the reduced one, okay, the left regular one, okay. So, well, these two objects, these two C star algebra, as we saw, there is a onto star homomorphism. So if you just let lambda to be the C star from C star of U to the C star lambda of G by sending a f into the, basically what is the image in the lambda of f, okay, or you take the pi u of f, the universal one, into the lambda of f, okay. This one is certainly an onto star homomorphism we just saw. So in other words, G is amenable if and only if this lambda is not just onto, but also an isometric isomorphism. And there's one little result about the C star algebra is that if you have a isometric, well, if you have an isomorphism between two C star algebras, then it has to be isometric. Okay, so any injective onto star homomorphism, it has to be isometric. So basically, we can say G is amenable. That's even only if this lambda map from your full to the reduced one is injective. Okay, so they're really the same. Okay, so being injective, that's also equivalent to being a isometric star isomorphism of C star algebras. Okay, we know it's already onto a star homomorphism. We just need the injectivity. Okay, so it turns out this is going to be a as you can see, this is a really nice theorem in terms of group C star algebra. So it relates the group C star algebra with this definition of amenability. So we're going to divide this theorem into the several steps, and this is technically true if you just consider any locally compact house rule, but as you already see, our focus is really on the discrete case. So let's just do the discrete version. So focus on the discrete G. So for non-discrete, there's not many reference. There's a classical textbook by Greenleaf. It's one of the some of the topics are actually from that book. You can take a look in there. It talks about the non-discrete case, basically all the locally compact case. The only difference is a lot of the finite support we have in the discrete case are going to be replaced by the compact sets. Okay, it's just a little bit more technical. So let's just assume everything is discrete. So the main theorem we're going to prove, we're going to divide this proof into several steps, is to prove the equivalence of the following several statements. So the first one is G is mutable. So let's say G is mutable. And it's equivalent to the following. So I actually have I can find a net, say psi I, sequence of the unit vectors in the L2 space. Well, here everything is discrete, so let's just use little L2 of G. So they are unit vectors with finite support. Okay. And moreover, I have that these have some approximation properties. So if I want to shift these psi I by the left regular representation, then they're not going to move away from the psi I too much. Okay, so in the L2 norm, they're going to converge to 0. That's for all s inside G. Okay. And thirdly, I want to say that it's related to the positive definite function. So we see the positive definite function, we actually define it on Abelian groups, and later on assignment define the operator values on non-Abelian groups. You can basically define a function to be positive definite if certain operator, certain scalar value matrix is positive definite. So it being amenable, in fact, is related to these positive definite functions. So there exists a net of positive definite functions, phi. So here positive definite means phi of the SI inverse Sj. If you pick any finite collection of these I and j, and you consider a matrix, n by n matrix, that's a positive matrix. So there exists a net of these phi alpha, these positive definite functions, so that it satisfies a few things. So first of all, phi alpha are the support is finite. Okay, so it has finite support, and moreover, it's going to have the it's going to be unital. So if you evaluate that identity, it's going to be equals to 1. And also, if you fix every element s, and you consider this net, this one is going to converge to 1. Okay, so that's pointwise. In other words, these positive definite functions are converging to 1 in the pointwise sense. All right. And finally, something about the main goal we want to show is that the universal one is isomorphic to the reduced one. Okay, they're all equivalent. And finally, I have the condition that the reduced one has a character. Okay, so it has a character. What is a character is that it essentially is just a one-dimensional representation. So there exists a pi from the C star lambda of G to the complex. It's a star homomorphism. Okay, so that's basically a character. Okay. So I'm going to divide this entire proof. As you can see, the main goal is really just to show the full and reduced. The number 4 is equivalent to, say, G is amenable.